there is asymmetric encryption, also sometimes called public key encryption, because there is a difference between public key encryption and symmetric encryption, or private key encryption. The private key encryption, there is only a private key. There is only a secret that cannot be shared.
Yeah,
right?
you don't share. That's why it's private, right?
And anyone holding that secret is able to both encrypt and decrypt. The beauty of public key encryption, or asymmetric encryption, or public key cryptography, or whatever we want to call it, the beauty of it is that it's based on a key pair. So we choose a secret. We always have to choose to create a secret, some random secret, okay? Exactly like the symmetric encryption, we have that secret. And then from that secret, we derive a public key. So there is a private key, and there is a public key that is derived from the private key.
You need to explain the derive term.
Yeah. The derivation is a one-way street.
Yeah.
It's a function that can only create public keys from private keys, not the other way around.
Yeah, you cannot reach to the private key if you have a public key, but you can generate any amount of public keys from a private key.
Exactly.
And keep going.
So there is this key pair that you can, an algorithm can help you create. So you as a user are able to create your private key, store it with your life as the other encryption mechanisms, but then you don't have to share it with other people so they can send messages encrypted to you, right? Mm-hmm. So this is a very big advantage, because you would have to create a bunch of private keys and store them and so on, so that you could have different channels to different friends.
Yeah.
And it would be a mess. If we only had symmetric encryption, it would be very difficult to implement encryption at all, right?
Mm-hmm.
And exactly because of that, as long as you have to share the secret with the third party, then your secret is exposed, right? Yeah. So anyone that you want to have an encrypted connection with will share the same secret as you.
Mm-hmm.
So if you use the same secret to everybody, then what's the point, right?
Yeah.
So you have to have different secrets, and then it would quickly add up and become impossible to address. So
and the asymmetric algorithms have they work just like this. Well, I have my private key, and I hand to you, to Pedro, one public key. Pedro encrypts the message with my public key, and I'm the only person that can decrypt that message, because I'm the only one that has the private key. Another advantage that this brings is that, first of all, it authenticates the sender of the message, because it was encrypted with that specific public key, and I can validate that. So
it's better the other way around. Let's think about the use case of having an email, for instance,
mm-hmm.
right? In order to have encrypted email, we need public key encryption or public key cryptography, because we have to have a way for multiple people to encrypt messages that we can decrypt, right? And that way we share our own public key with the world. So mm-hmm. everyone knows, and we will talk more about this later in the episode, but generically we will share a public key with everybody. So everybody can encrypt messages for us. But what happens when we want to reply to them, right? The other people, the other party that we want to send a message to, replying, they also share their public keys with the world,
Yeah.
right? So when we want to write a reply to that person, we will encrypt the email with their public key. But before we do that, we sign the email with our private key. And that's the way that they receive the email and they know that the email is from us because there's a signature there. And that signature is encrypted with their public key and alongside with the content of the email, right? So that they can decrypt it. So they decrypt it and they know that it's for them because the decryption works. Otherwise, it wouldn't work, right? Then they validate the signature and they say, okay, this is really from that guy because only a guy with a private key that corresponds to this public key
Yeah.
is able to sign the content, and that's it. So
Yeah.
basically, the functions of a public key is allowing encryption, right, and signature validation,
Yeah.
right, and the role of the private key is to decrypt
Yeah. And sign.
and sign.
Yeah, only one thing that is missing there is that you will need the public key in order to verify the signature of the contents.
Yeah.
So, and this is so beautifully done that when you try to verify, well, when you are signing, you are putting your email there, and when you are verifying, the result of that verification will be your email. So it's something like this.
It is. It can be implemented in various different ways. We just need the public key to validate the signature. That's it. And as long as that public key is associated with the email address, we know that it comes from that recipient. That's it.
Yep.
But it can be there can be extra validation on that and so on. It depends on the level of security you want in your communication, right? But as a rule of thumb is just that. The signature validates the origin, public key, right? And the public key of the destination is the one that is used to encrypt the material, the communication content. And then on arrival, the private key is used to decrypt the content, and the public key of the origin is used to validate the origin, exactly, because there is a signature there that is verifiable with the public key. So by doing a signature verification, we supply the public key, and the result is, okay, this is a valid signature, or not okay, this is not a valid signature, because this signature is not was not made by the private key that corresponds to that public key that you are saying. Right?
Yeah. Yeah. Now,
so
regarding asymmetric encryption, there are two main encryption methods, which are RSA and ECC. Do you want to go a little bit on the differences between the two of them?
Yeah. RSA is the regular public key cryptography that we use in many other use cases, and ECC is a particular type of public key encryption which is based on an elliptic curve. So this means that there is an elliptic curve, and that when you draw a line on the spectrum of things, it usually intercepts 2 points on the elliptic curve. one one side and one on the other side. And um, this is getting this very very basic. Um, the the idea of the ECC, the elliptic curve cryptography, is that there is a correlation between one point and the other point of that intersection with the line, so that one point corresponds to the value on the private key and the other point on the other side corresponds to the public key value, and so on. Imagining a very big private key, then a very big public key will be generated by this math with a factor that also creates more randomized output. So that's it. But it's always the same idea. From the private key, using this method, we will create a public key and not the other way around, right?
Mm-hmm.
It's basically the same thing. The method is different. And for us to understand what does this mean, for instance, Bitcoin uses an elliptic curve cryptography algorithm, which is SecP 256 K1. And that means that to have the same security, if it would use RSA keys, instead of 256 bits, it would require 2048 bits in an RSA key to have the same security because of the algorithm, right? So this is why the Bitcoin and mostly all the crypto things are implemented with ECC because it's more efficient. It has less, requires less storage for keys because the keys are
it
much
requires
shorter.
shorter keys in order to be safer.
Yeah. So this is it. Mostly in a very high level, without entering too nerdy stuff. This is why we use elliptic curve cryptography in blockchains instead of RSA.
We don't want to get too much in the weeds with this.
Yeah.
Because this is math, and it kind of sucks.